All right, welcome everyone for high performance computing. Today we have practical lecture 10.2 about distributed deep learning, and we have an invited speaker here, Rocco Sedona, who is a PhD student here at the University of Iceland in collaboration with the Jülich Supercomputing Center in Germany. He's also a member of the Simulation and Data Lab Remote Sensing. He will also introduce. And Rocco, yeah, please get started and inform us about the interesting approach of distributed deep learning that can really leverage HPC enormously.
Thank you very much, Maurice. Hi, everybody. I'm Rocco Sedona. And as Maurice said, I am a PhD student at the University of Iceland and also at the Forschungszentrum Jülich. And I'm also a member of the Simulation and Data Lab Remote Sensing, which is partially funded by the EuroCC initiative. And as Maurice said, I am in between I'm a PhD student at the University of Iceland, but also working on the very powerful supercomputing machines of the Jülich Supercomputing Center, which puts me in a position where I can do some very interesting things in research. I am one of the members of the Simulation and Data Lab. The other ones are listed here, and there is the head, who is professor now, full professor Maurice Riddle, and also my other supervisor, Dr. Cavallaro, who will speak in the next lecture, and also a new member who is Surbhi Sharma. So I will now go ahead with the introduction and trying to explain where my lecture is located in the context of this HPC course. So this lecture will be a practical lecture, which is actually lecture 10.2. And what I will explain will be, in a way, a mixture of theoretical concepts related to what I do, which is, once again, distributed deep learning, and also some hands-on, so some more practical concepts, practical applications in my field, which is remote sensing. But also I will try to show some of the ways you can actually leverage some frameworks you can leverage to distribute your deep learning models. So I want to stress this point, which is very important, that some of the concepts that are crucial in my lecture are very much related to lecture 2 and practical lecture 2.1 and 5.1 of this HPC course by Professor Riedel, because much of the base upon which these frameworks, these distributed deep learning frameworks, are built is mostly MPI. So I hope that by now you have already started and learned something about it, which you did, I'm sure, because it's very important to what I will say later. So why it's locked? Okay, so I will now review some of the concepts of the previous practical lecture 10.1 by Dr. Cavallaro, since they are very important to what I will say then today. So we are working with with deep learning, so models such as the multi-layer Percepton models that are an ensemble of nodes, of edges, and the connection of which is our model. In my talk, I will mostly treat the problem of classification, but you could in principle use these multi-layer deep models in other ways. For example, you could do segmentation, which in computer vision is another popular task for deep learning models. But again, today I will talk mostly about my application, which is classification application. So you can see here, reviewing the lecture I think it was slide 12 from Dr. Cavallaro's slides. You can see the model, and on top of the model, a classifier that gives as output our probabilities for each class of our classification task. So an important thing about deep learning models and explains why they are so much widely used now is that modeling using nonlinear functions, they can actually approximate any kind, in principle, any kind of function. So they are called universal approximation. This is a universal approximator, and this is a very central concept. So as I said, these models are made up of edges, so of connections between the nodes and nodes themselves. And as you should recall from previous lecture, each node comes with an activation function. So activation functions are operations that are performed on the input coming from each edge to the node. So this course is not obviously it's just an overview on some deep learning models and deep learning techniques. But what is very important to understand is that there are some functions, and they're mostly nonlinear, as I said, to approximate the any kind of functions that you like. And in particular, if you look at these 6 functions that you can see listed here, that are just some of the many existing ones that are used, it's not that you can use each of them for any task. You will have to select the one that performs better for the role that it has to play. So for example, just as an example, this sigmoid function here will be used mostly in the last layer, so in the classification process, but you most likely will not use it during the training of your model inside as an inner in an inner layer of the model. On the other hand, what is mostly used is this ReLU, or also very popular now, the leaky ReLU function. So another very important concept that you should now know is what we are doing. So what are we talking about when once you have your model, what do you want to do? How do you train it? So why is this training important? Why you have to train a model? Because your model, when you initialize it, will have most probably random weights. So if you try to predict something using that model, you most likely will get outputs that don't make much sense to solve your problem. So what you have to do is to train, so perform this training of your model, and in this way tune, optimize the weights and bias values, which are the parameters of the model that we want to learn. And how we learn it is done mostly nowadays with this algorithm that is called backpropagation. So given these loss functions that computes an error between your expected true output and the output of your model, you compute this kind of error and you try iteration after iteration to reduce this error, optimizing then the parameters of your model. So a very important thing to remember is that this is an iterative algorithm. So it's not done all in one step, but it is done in many subsequent steps. So here again, recalling concepts of slide 14, this time of Dr. Cavallaro, this is how actually the algorithm performs this optimization of the weights. Just a clarification on the term mini batch gradient descent. So Nowadays, many people use different terminology because deep learning has evolved at a very fast pace, and for a long time now, because it started to grow a lot in the 90s and then had a second wave in the late 2000 and something, 2010 mostly. But so by meaning batch gradient descent here, I will also mean what you could find with the name stochastic gradient descent. So I might sometimes later on refer also to that as a SGD, or stochastic gradient descent. So again, if you look at the figure, what we want to do is to hopefully converge to a minimum of our loss function, so of our error, so to minimize this error, and find the weights. So you do these, you go on with this iteration through your data. You pick a batch of data. So a batch is simply a group, a subset of your training points, of your data points that you use for training. You have to compute the gradient of the loss with respect to these parameters that are our weights. And once you do that, the next step is to update the weights that you had from the previous step, how multiplying this gradient by this term eta, this Greek letter eta, that is called learning rate. And then obviously you update these weights, as I said, and you go on for all the data points of your training set. And you actually, and these are called iterations, as you can see in next slide. Actually, you have to go through your data set not just one time. So the number of iterations that covers all the samples in your data is usually not enough. So you will have to do this multiple times, and every time you do this, so you go through your data set once, is called an epoch. So I will use this term epoch, I think, a lot in the next slides. And another key concept that is here in this slide is that models, okay, I talked about finding the optimum values, so the optimum parameters of our model, and I said also fitting the model, but it can happen, and it's quite common actually, that your model is not performing well, and in a way you have to diagnose why. And there are two modalities of failures, I would say, that are represented on the left and on the right of our optimum, which are overfitting, so fitting too much our data, and underfitting. So underfitting would mean, on the other hand, that our model is not capturing the pattern or the distribution of our data correctly. So what would happen once you deploy models that are not well optimized is that you see in this other figure, during validation, so when you test your model, you would definitely see the error increase a lot, and we want to avoid that. So now I will revise some other concepts, not from the lecture of Dr. Cavallaro, but from lecture 2 of Professor Riedel, and specifically slides from 19 to 23, recalling important concepts of MPI, because then, as I said, MPI is the base upon which our frameworks for distributed deep learning are built. So MPI, you already know, is a standard for what? For exchanging messages between multiple processes. So we are in a distributed memory setting, and it implements actually many collectives, so many communication operations that are point-to-point, but also can be all to some, all to one, one to all, and many different and many different topologies can be implemented in this way. And that's important because then, as I said, Horovod, which is one of the frameworks I use most, is built upon the ring or reduce algorithm that is nothing else than a topology that is easily implementable with MPI. So these slides will be very fast because, as I said, they are from lecture 2 of Professor Riedel. So exchanging data between processes. So as I said, there are operations one-to-one, which is the simplest one. But then there is, for example, the broadcast operation, where one process sends the same data to different processes. Then there is the scatter. So scattering a data means, scattering an array means sending different chunks to each process. Then there is the contrary operation of collecting on one node the data from other processes. And there is also this operation called reduction, which computes something with the data that you collect. And I wanted to recall these concepts because, once again, the ring or reduce algorithm features these different steps of sending information, collecting, and then performing a reduce operation in the end. To do what? To optimize the parameters of our model. So you know MPI, but there are obviously other backends for collective communication. One that is very much used on GPUs is Nickel. So I have to say that MPI can be used with GPUs, but Nickel is, on the other hand, specifically designed to work with NVIDIA GPUs, and it provides optimized optimized operation on the NVIDIA GPUs with higher bandwidth and lower latency compared to other backends, which are, again, MPI. But there are also other backends that are used. For example, Glue is another one that is widely used with PyTorch. And I suggested that if you are interested in that, you look at this reference here, this GitHub repo that I put, because there are many interesting charts as the ones that I put here, that I pasted here, comparing the different backends in the setting of when we want to solve the task of distributed deep learning. But here in this figure here, you can simply see what happens if you use these Nickel optimized algorithms on the NVIDIA NVLink topology. And you can see that compared to other settings using even simpler Ethernet, gigabyte Ethernet, but also InfiniBand, the use of Nickel can increase a lot our performances in terms of bandwidth. So I will now start another part of my lecture, which is trying to introduce you to some of the key concepts of distributed deep learning. So as I said before, I was a bit recalling concepts from previous lectures, but also extending them in the way that I needed to go on with my lecture. But now I will go to that part, which is mostly related to my research. So there are many ways of doing distributed training, and the difficulties that come with them are different depending on the strategy that you adopt. So the most widely used up to the moment I'm talking is called data parallelism. So what you do is, given that you have multiple nodes, for example, with the GPU on each node, you copy the same model on each device, on each GPU, but you divide your data in chunks so that each model on each device will see a different subset of the entire training set. And during training, these devices will exchange the gradients, so will exchange the parameters, so that the models between the devices are actually sharing the gradients, so are consistent across each device, which is very important because you wouldn't like to end up with a model that is different on each device in the end. So different data as input, but you want to end up with the same model after this sharing of the weights of the parameters. So another slide on this concept of data parallelism to explain you a little bit more where these operation takes place. As we were revising and recalling again MPI, it's used here. So you see different, at the beginning you have a different model. Well, it's actually the same model, but with different parameters. And they compute the gradients independently on different sets of the training, of the original training set. And then the gradients that are computed independently are averaged, so that once this average operation, which is computed with this MPI or reduce operation, is done, here at the end of this process, you end up with a model that is consistent. So now, if you start with models that have different parameters, after this or reduce, you end up with a model that is consistent across each node, which is very important once again. But I will explain more on these when I will talk about Horvath anyway. So there is another way of distributing your training, and it's different from data parallelism, and it's called model parallelism. In which way? In the way that here you don't split data, different chunks of data across among the devices. Rather, you split the model itself. And it's no wonder that, I mean, it's not a surprise that you can understand why this is much less done up to now. That's because it's much more complex to distribute a model that has many interdependencies between the layers across multiple devices. And kept aside the technical difficulties, there is also a problem that doing so, you increase significantly the amount of communication that is needed between each device. So it is much less used because it is much more difficult to optimize from a technical point of view these kind of models. But things are starting to change, and I will also speak about DeepSpeed, which is a newer framework than Horvath from Microsoft that tries to address this issue. There is a third strategy, but it's a rather general term for distributed training, which is called pipelining. And when you read papers about it, you have to be very careful, because by pipelining, people mean different things. So they can mean a way of pipelining the data, so the input, and in this way, you could see it as a way of referring to the first strategy that we have seen, so the data parallelism. On the other hand, you might see somebody calling pipelining the fact that you train, you in a way stage your model and you send different layers, subsequent layers of your model to different devices. So in a way, you pipeline the model in the sense that first you train a part of your model, then you train as the second part, and then the last layer, for example, which are on different devices. And in this way, you could relate it more to model parallelism. So just the takeaway from this is be careful when you read pipelining, try to understand better what is meant. Okay, everything is very nice, and everything would work probably very well, you think, if you just copy paste your code and distribute on many GPUs. Well, unfortunately, it's not so easy. There are some open challenges that are being addressed by many scientists around the world. And the most important one is, I would say, this, that is shown in this figure, which is the fact that as the size of the batches you are using increase, the models tend to have more difficulties during training to capture regions of optimal regions to minimize the loss function. So this is a very mathematical question. There are some very interesting papers on that. One is by a very important professor who teaches in Switzerland. And I've put here the reference if you are a lot into math. But yeah, what happens basically and intuitively is that instead of ending up in a flat minimum, so in a very stable region of your loss, if you use large batch sizes, you end up in sharp minima, which are very unstable and give you very often problems of overfitting, if you recall what it means from previous slides. And you might wonder, why should I use so large batch sizes? Well, this is a consequence of the fact that you want to distribute your model on probably on many GPUs. So what is important is not anymore the batch size you use on your single device, but you have to think that once you distribute your model on many GPUs, your batch size, your global batch size, is not anymore the local batch size on each device, but is the multiplication between the local batch size on each GPU by the number of GPUs. So it means that if you want to use many GPUs, it's very easy and very quickly, you end up with very large batch sizes, which give very likely this kind of problem. So this second problem, which is called optimization difficulties, is now very well addressed by newer optimizers. But this issue of generalization shown here in the picture is still unfortunately very pressing and not so easily solvable, and still a lot of research on that. And also there is a third issue, which I would call more technical, so less scientific, but more technical, related to the architecture topology of the machines that are used, related specifically to the latency between the nodes. So if you increase the number of nodes, then the efficiency tends to decrease, because obviously the amount of communication, increases with respect to the computation. So now there are some techniques to try to address this issue once again, and we don't have much time to go into the depth of it. But one very popular method that is used also for other tasks is batch normalization, which tries to solve a problem called as internal covariate shift by doing what? By subtracting the mean of each batch and normalizing each batch by the variance. And this is a form of regularization. So regularization means trying to reduce the problem of overfitting. But there are so many other techniques. It's just to give you an idea. Here in this slide, I want, on the other hand, to tell you that there are many ways of performing this update during the data distributed training. And there are, yeah, mostly two families of approaches that are the synchronous or asynchronous approaches. So in synchronous approach, every process does an iteration, so go once through your batch, and synchronously each device exchanges the gradients and performs the average, and it goes on synchronously in this way till the end of each iteration, till your epochs are over. On the other hand, there are also asynchronous methods which can be faster but don't guarantee convergence, actually, which is quite a pity because convergence is important. So convergence means that we might end up in asynchronous methods with a model that just is not optimized, or that is not stable. But each method has its own drawbacks and pros. So in general, synchronous, I would say, is now anyway the most widely used. So again, this is a technical slide on how this gradient update is performed, and there is this way of having a central parameter server that takes care of gathering and sending the updates of the gradient. It was widely used in the past, but as you can imagine, you can easily see, it's not good because you have one single point of failure. So if this parameter server, with the increase of devices, becomes very much overwhelmed by the amount of communication, then it might become very slow or even eventually fail, crash. So a solution that is actually very much implemented is one that I will present later on in the second part of my lecture of today. While now I will go on with some other strategies that we use to try to address this issue I was talking about, which is related to the size of the batch. So you should remember from the first slides what the mini batch gradient descent algorithm is, also called SGD, which is a general name referring to many different things actually. And here in this slide we are trying to see exactly how these weights are updated. So you should recall how it's done. So simply taking the gradient of the loss, computing the gradient of the loss with respect to the parameters of our model, and we update the weights by subtracting the multiplication between these gradient and the learning rate, which is eta. So when the problem is that if you use very large batch sizes, once again, you have to, in a way, try to adapt your learning rate in a way that it makes sense, so that your training becomes not too slow and even not too fast. And there are some heuristics, so some ways of doing this. And one very simple is shown here. So in this second formula here, you see what would be the update of the weights after k steps compared to the update after one step if you take a bigger leap. So here in the second formula, you have many leaps with a smaller learning rate. In the third formula, you have one single leap, but with a probably bigger learning rate. And how do these two formula become the same? So how can you adapt your learning rate? Researchers proposed this. So this learning rate, when you use larger batch sizes, should be adapted in this way. So eta at, which is the new learning rate, should become simply computed linearly as a multiplication between the original learning rate and the number of devices that you're using for your distributed training. that's a very simple approach, but there are more complex approach to decide which learning rate to use. And another one, which is less aggressive, is not computing the learning rate linearly rather than using the squared root of the number of devices, or anyway of the number of the size of the batch. They showed this mathematically in some papers that it makes sense to do so to keep the covariance matrix similar, using again one leap with bigger learning rate compared to multiple leaps with smaller learning rate. There are, okay, before stopping, there are some 2 more slides on the strategies that can help a lot. And one is another strategy that is widely used is warm up. So instead of starting off with a very high learning rate from the beginning of your training, you try to start in the first iterations, in the first epochs, more precisely, with a smaller learning rate, and then increase it gradually till you reach the maximum of the learning rate. And you do so to try to reduce the oscillations of your model in the early stage of training, and try so to avoid instability. Yeah. Yeah, another way to do so, to reduce instability, that is once again caused by this sharp minima that I showed some slides ago, is using this new optimizer that is called LARS, that instead of using a global learning rate that is used just for each iteration and for each layer, it tries to adapt it how with this mathematical formula as the ratio of the norm between the weights and the norm of the weights and the norm of the loss, making this for each layer, so for each layer of our model. And this has proven to be very good for convergence when you use very large batch sizes compared to the original SGD algorithm. And then we will go to our last slide of this first part, which is another technical issue related to distributed deep learning. So as I said, if you recall, a big issue, a big problem is communication time compared to computation time. That's crucial to have to try to reach some sort of efficiency when you train, so not to waste your resources, your GPU time. And so what Tensor Fusion tries to do is trying to maximize the throughput and reduce latency, packing smaller gradients into groups of bigger tensors before exchanging them between the devices. And in this way, you can reduce the amount of time that is spent for communication, to communicate small tensors between the nodes. And again, if you look at the paper that I put there when I was talking about Nickel and CCL, it's very, if you are interested, you should have a look at that, because they compare these different backends for communication, MPI, Nickel, Glue, regarding also the tensor size, which is again very crucial. So I want to conclude this part of the lecture also telling you to have a look at some of these references if you are interested, because they can tell you probably much more than I can now in these 40 minutes. So thanks a lot, and see you later.
Yeah, thank you very much, Rocco. That was very interesting. And yeah, we reconvene for the second part in a couple of minutes.